I think we should be alright. Thanks.
That's all good.
Sorry for the
No worries.
Not stuck in traffic.
Yeah, no, you can't help that. It's no problem. We're all good. And here we are back in space again. So over here, this is Proxima Centauri, a tiny red dot, a red dwarf star. You can see that even if you had a powerful telescope such as with the European Southern Observatory, without the white circle in space, you'd still be struggling to find that tiny star. Alpha Centauri A and B are obviously two stars, but be very saturated in this picture, trying to get all these other stars. That's just going to saturate the image. So it looks like one star, even though it's two over there. So it turns out that Proxima Centauri is the closest star to our Sun at about 4.25 light years away. So Proxima Centauri then just at 4.37 light years away, Alpha Centauri A and B. Proxima Centauri has been confirmed to actually be part of the system. It was thought for a while that it might have been just passing by. But if it was passing by, you'd be able to tell from the speed it's going whether it was bound to the other two. It was found that it only had about half the energy required to escape, so it must have been orbiting the other two, and it definitely is a three-star system. And it's about 20% of a light year away from Alpha Centauri A and B at the moment. Now, if we want to zoom in, first of all, to these two, Alpha Centauri A and B, they take about 80 years to orbit each other once. At their most distance, they get about 3 times as far away as Saturn to the Sun, and probably about as close as Saturn and the Sun when they're at their closest. In about 10 years, they'll be here and here, so they will be at that closest point, and they're just heading towards that now. So 10 years' time, they'll be as close as they get. Now, if we look further out at Alpha Centauri C or Proxima Centauri, that takes about 500,000 years to orbit the other two. So at the moment, it's about the most, about as far away as it's going to get from the from A and B. And in 225 million years, it'll be at its closest point, about 0.07 of a light year away. So it's a pretty huge system of stars. So we'll move on a little bit now to Gamma Crucis. Gamma Crucis is about 89, 90 light years away from us. And this one is a red giant star. It's used up the hydrogen in its core, and which is what stars burn for most of their lives. They burn hydrogen or fuse hydrogen into helium. Once they run out of their hydrogen, the helium will now start fusing into heavier elements, and they will puff up into a large red giant star. So this star, Garcrux, is its more common name, much larger than the Sun. This one, of course, doesn't have any planets, but it's still pretty cool to know that that's about 90 light years away from us, and it's the top star of the Southern Cross. Well, if we look at the Southern Cross from that angle, of course. Next, we look at Epsilon Crucis, about 230 light years away. Also a red giant star. Its name is Jonathn, and this is an Aboriginal name meaning bag of songs. Now, apparently, the Aboriginal name for bag of songs was meant to be Alpha Crucis, and this one was meant to be Wuja, or fire, but it seems that a slight mistake was made, and now the common name for that star is now Jonathn, and it can't really be changed now. But it is Jonathn is now its name. So that's our second red giant. So these are the two closest stars to us of the Southern Cross, these red giant stars. So now we're going to move to our first hot blue stars, and we'll start with Beta Crucis, also known as Mimosa. This is at least a double star, possibly has 3 stars in its system. So Beta Crucis A and Beta Crucis B. And hot blue stars burn a lot faster and a lot hotter than our Sun, and so they have a much shorter life. The reason being they're so large that the gravitational force on the core means there's a lot more pressure. Fusion happens faster, so they burn through that hydrogen a lot quicker, then move to the next part of their life. So these stars are very hot and bright, and it's no coincidence as the further away we get, we're kind of getting hotter, brighter stars. because if they weren't hotter and brighter, they'd be dimmer and dimmer and we wouldn't see them. So the further away they are, the brighter they're going to be if they're going to kind of look like a constellation to us. Now, Alpha Crucis, this one is at least a 5-star system, possibly 6. Now, it does get harder and harder for astronomers to make out numbers and sizes of stars the further away we get, especially with these distant multiple systems. So this one, with its 5 at least, bright blue stars, it's almost like a planetary system, but with stars, except with a planetary system like our solar system, the sun is 99% of the mass of the solar system. So the planets orbit the sun, and the sun does wobble a little bit, but in that system, there'd be no star in the centre, they'd be orbiting the centre of mass. So Alpha Crucis AA and Alpha Crucis AB would orbit each other, then Alpha Crucis B would orbit that pair further out, and then CA and CB will orbit each other as a little group, and then that group will orbit the other. So quite a complex system. I've got another system to show you a bit later where I've got a bit more of a map of what's happening. And you'll be noticing now there's quite a few multiple stars in this. At least half, a lot more than half probably, the stars we can see with our eye, with the naked eye in the sky, are multiple star systems. So they're very common. And so we'll go now to Delta Crucis, or MI, another blue star. This one is a single star on its own, as far as we know at this point. But now we'll go ahead and have a look at Beta Centauri. Beta Centauri, the friend or the other Centauri with Alpha Centauri, is also a triple star system. These stars are a lot bigger than the stars of Alpha Centauri, of course. So Beta Centauri AA and AB, again, will be orbiting each other, with the smaller one, Beta Centauri B, a bit further out. So just to summarise that multiplicity of those stars, we see 7 dots here with the 2 pointers and the 5 brightest stars of the Southern Cross. So we have 3 here, 3 stars here. If you add them up, you're probably looking at about 17 stars when you look at those 7 dots. So it's not just 7 dots in the sky, it's 17 at amazing different distances. With this one the closest, that one the furthest away, and those ones in between. So it's not just a Southern Cross painted on a dome, obviously, as we all know. And I think probably, again, the takeaway for this one, if you don't want to have to remember too much, I just think remembering that close and much further away is quite amazing when you go and look at it next time, just to know how far they are away from each other. And if you're wondering how accurate these distances are, they're pretty good, but some of the data from the Gaia satellite, as I mentioned earlier, some of them are a little bit hard to know the distances too. Some of the data from the Gaia satellite meant that the brighter stars saturated the data a little bit, so it was very hard to get their distances. So that's why it might be about 2030 before a bit more analysis is done and we get some better details about the distances to these other bright stars. And just in case you're wondering why I used that particular coordinate system, no reason really. It was just the best way to do a little model that kind of looked easy to look at. So if you took that and put it up here, if we were standing in New Zealand looking up directly from there, that's kind of the angle it would be. But of course, it also depends on the time of night, because as the Earth rotates, it's going to move around. But yeah, there's no particular reason to use those coordinates, except that it kind of works well for this presentation. Now, since we're talking about distances, a good question to think about is, what is a light year? Well, the speed of light, first of all, is about 300,000 kilometres per second. Now, light year is the distance that light travels in a year in a vacuum, so it's through a vacuum. So a light year is a distance, not a time. So that's nearly 9.5 trillion kilometres. And just to put it in perspective a little bit, if we were To take a light beam, after 1 second, it would get about 80% of the way to the moon and takes about 1.25 seconds to get to the moon. The sun at 150 million kilometres away is about 8 minutes and 20 seconds of light travel time. Now we get to Alpha Centauri. Of course, that's 4.37 light years away, so it takes 4.37 years for light to get to Alpha Centauri to us, or the other way around, and that's about 41 trillion kilometres away. And Beta Centauri, of course, 360 years, and that's about 3.4 quadrillion kilometres. That's probably starting to sound like blah, 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 zillion, kind of weird numbers. So that's that would be 3,400 trillion kilometres, so a long way. And maybe something that's a little bit easier to think about, not that easy, but a bullet going maybe at 4,000 kilometres an hour, going pretty fast. If you imagine that going past you, you wouldn't see it. That would still take 4 days to get to the moon at 4,000 kilometres per hour, about 4.25 years to get to the sun, to get to Alpha Centauri, travelling at that speed, 1.2 million years, and nearly 100 million years to get to Beta Centauri at that speed. So we want our spaceships to be much faster than 4,000 kilometres per hour, obviously. So it'll be a while before we can actually go there. Of course, with relativistic effects, we get there pretty much in the lifetime of the people in the spaceship, but we have to design a spaceship that can get that speed closer to the speed of light anyway. So let's move on now to another constellation. This one's the constellation of Orion. So a little bit different to what we did before, just for your sanity, so you don't have to go through exactly the same kind of thing again. So we'll have a look at a handful of stars in the constellation of Orion. There's a lot more stars in this constellation. So first of all, does anyone remember what that orangey star down there is? Betelgeuse? Yep. And what's going to happen to that? Anyone know in the next 10,000 to 100,000 years? Yeah, that's right. That's going to... Of course, we'll have to sit back and wait for a while, so who knows, it could be 10,000 years. Oh, there he goes. Now, it should explode as a supernova. It will be a problem for Orion. That was the shoulder up here, except up the other way. So that's going to ruin that one. But when that does explode, the core will become a neutron star. So although we will lose a star there, we'll know that there is now a neutron star sitting at that point in space. There's a small chance it could become a black hole, but calculations show that its mass is not quite enough to form a black hole, so a neutron star should be the result of this supernova. So Betelgeuse, as we looked at, 540 light years away, plus or minus 100. So nice error bars there. Then we have Bellatrix at 250, Scythe 650, and then Rigel 860 light years away. Now the stars of Orion's belt, Mintaka, Alnilam and Alnitak, which I usually call Alnilam and Alnitak because it's easier, they are all probably about the same distance away, 10 light years or so. So they look like they're a group, and they possibly are a group as well. It is possible that Alnilam or Alnilam is 1900 light years away, but the data at the moment seems to point to them all kind of being that distance away from us. So this one, Orion Nebula, of course, is not a star. It's a cloud of gas and dust where there are a lot of new planetary systems forming. It's a stellar nursery, and we'll have a look at that one shortly as well. And Hatisa, about 1630 light years away from us. So we'll go this time over that way and look back at the stars, looking from a different angle. And you can see again, it's kind of meaningless, except for maybe Orion's belt. And if we have a look at the lines, some of the imagined lines in Orion, and put these on the image here, you can see again, it doesn't make a lot of sense from this direction. And if we go over the top again, you know, it's relative, what's over and under and around. You can see, for example, that the sword is just a meaningless mess, but the belt again is kind of 3 stars in a row, if that is in fact the distance to the middle star of the belt. So here's a 3D model for these stars again. So Probably this would be where it would be good if we could actually draw the stars at their actual size. These are still much too big for their actual size, but if you could draw them their actual size, it would give a better idea of how big the Orion Nebula actually is. It's about 24 light years across, so it's a very large area, whereas the typical large star is less than 1,000th of a light year in size. And there are hundreds or thousands of stars in the Orion Nebula. And again, remembering there's many other stars out there. I guess if you were looking from a different direction, you might be able to use those 3 stars as a belt of something. So a quick look at a selection of these stars, and we'll start with Mintaka, the first star of the Orion's belt. Again, this is another 5 or 6 star system. Mintaka AA1 and all those numbers. The letters are really meaning that, for example, Mintaka AA1 and Mintaka AA2 and Mintaka AB was probably thought of as one star, Mintaka A to start with, and then thought of as Mintaka AA and AB, and then they found probably that those 2 stars were separate and not just one star, so just kind of numbering and lettering them as we find more. So this one, we can have a bit of a look at what's happening. There was a paper in 2023 that gave an idea of the orbits of these stars. So these 2, the main 2, orbit each other in about just under 6 days, and they're about the distance between our Sun and Mercury, about 0.4 of an astronomical unit. 1 astronomical unit is the average distance between the Sun and the Earth. So it's not to scale, and this is why. If it was to scale, I'd have to draw these 2 like that one 172 screens up that way, and about 18,000 screens that way, so quite a long way away. So I didn't bother drawing them to scale. So this one here, Mintaka AB, about 152 years to orbit this pair, and then the pair over there orbiting each other at a period of about a month, and they're about the distance between the Sun and Venus. And that pair orbits this triplet here over about 10,000 years. Mintaka B may or may not be in the group, so I've just put a question mark next to that one. So the orbits themselves are these 2 are orbiting the centre of mass, and this group, the centre of mass, will be orbiting the centre of mass of that star, so it's getting messy already. You can see this group is going around here. The other 2 over there orbiting each other's centre of mass, CA and CB, and then that group will orbit that group around the centre of mass of everything else. So if you were on the star, you'd be going around kind of a spiral within a spiral. So it's pretty amazing, really, quite a neat thing to imagine what's happening. And if I could do an animation of that, I would, but it'd be rather tricky to animate that one. And B is just sitting there because no one's quite sure what's happening with that one. So if we move on to Alnilam, that's about 4.5 million years old. It's at least 430,000 times as luminous as our Sun, with a surface temperature of about 27,000 Kelvin, which is about 27,000 degrees Celsius. The Sun is about 5,800. So much hotter, brighter and larger than our Sun. Now the third one in the group, Alnitak, this is another multi-star system, so that's probably 3 hot blue stars. And now the Orion Nebula. So we'll zoom into that. That's about 1,340 light years away from us. Now we know that there are planetary systems forming in the Orion Nebula, about 180 protoplanetary disks, which are disks of dust around a newly forming star. And here are some photos of some of them in infrared imaging. The top one, you can see a nice disk forming around a star. Some of them are kind of getting a little bit damaged from hot stellar winds from other stars, so any planetary disks may be destroyed before planets can form around these. So we know that there will be lots of stars and planets in this in this nebula. Those 3 stars there are not Orion's belt. I think sometimes they call it Orion's mini belt, if I'm right. But sometimes it is good, yeah. And when you look through telescopes, sometimes you can kind of see those. And first time, I know a lot of people say, "Oh, is that Orion's belt?" Because it's quite hard on the brain to kind of work out what you're looking at when you zoom in into these. But there's quite a bit more happening in Orion. There are things called jumbos, Jupiter mass binary objects, that were discovered not too long ago by James Webb Space Telescope. Now, there's about 42 pairs of these have been found so far. Now, these are rogue planets, so they are planets without stars. So this picture here, a mix of infrared and a bit of visible colours. So you can see a pair here, another pair down here, a pair up there, a couple more over there. Now, they're called Jupiter mass binary objects because they are within a few times the mass of Jupiter. For example, up the top, 3 and 7 times the mass of Jupiter, 4 and 3, and they're probably about 100 or 200 astronomical units apart. How they formed is a bit of a mystery at the moment. Whether they got ejected from a star, which would be quite weird for 2 planets to be ejected from a star and stay together. So that's a bit of a mystery. Or maybe they formed as pairs rather than a star forming. Just enough gas and dust to form these planets as pairs. There's also some triples. Triples have been found as well. So I guess if they're sitting or living in Orion Nebula there, they're probably all around the galaxy and around the universe as well. So it's a really interesting new thing to have discovered. I suppose if they had moons orbiting them, and then with tidal heating, you might have icy moons that could have maybe oceans and life, if we speculate a little bit further. So yeah, it's still a bit of a mystery, that one. So Betelgeuse or Betelgeuse. Now, Betelgeuse or Betelgeuse, depending how you like to say it, I'll just stick with Betelgeuse from now on. Its diameter is probably about 70% of the orbit of Jupiter, so if we put it into our solar system, it would reach out almost to Jupiter. It's not a nice spherical star, as you'd expect. If we look at a simulation of a red giant star, they're kind of like bubbling, boiling gas. That's sped up. You can see the years going past at the top. So that's probably the idea of what it might look like if it was very much sped up. And if we looked at it in real time, it would probably look a bit like it had just stopped there. Now, Betelgeuse will have a large atmosphere of gas and dust being puffed off. And a little while ago, it was thought that it may have a little companion star, and just recently some imaging has been done of this companion star. Does anyone know what that might have been? It was given kind of just a fun name. Does anyone know what that name was? It's a friend of Betelgeuse, like a buddy. Beetle Buddy. So it's called Beetle Buddy. And this is some actual imagery here from Gemini North Telescope. So that's Betelgeuse. That's the companion. There is a possibility it's just noise and not actual data, but being a star does fit with a lot of observations, such as why Betelgeuse was dimming and brightening a little bit in the past at some stage. So it seems like it's a good chance it's there, but there's still a small chance it's not really there. Beetle Buddy will, of course, not survive a supernova. So Beetle Buddy won't last 100,000 years. Even before that, it's thought that because if it's actually going through the outer atmosphere, it's probably going to be there'll be a bit of drag, so it'll probably spiral into Betelgeuse. So someone said to me, why do they give it such a cute name if it's going to have a sad end so quickly? But it's quite neat to know that there could be a little star out there as well. And finally, the blue giant Rigel, which again is a multiple star system, a very large blue star with 3 smaller blue stars, still bigger than our sun, but 3 smaller blue stars. And the idea of how the orbits for this one might work is another complicated one, with the main star Rigel, and then probably about 2,500 astronomical units away, a group of 3, taking 24,000 years to orbit the main one, and then a pair, BA and BB, taking about 10 days to orbit, very close together, half the distance between the Sun and Mercury. and then the third star about 26 astronomical units away, taking 63 years to orbit. So all these multiple stars will have really fascinating orbits if you're kind of into that kind of thing, and I think it'd be fascinating to see what each of these are doing. And again, the distances were not to scale for that last picture. So a bit of a takeaway from this, from the Orion constellation here, it's probably the fact, what's the easiest, you can get rid of some of those, probably the fact that these outer four bright stars are closer than the rest of them. These three stars, the belt, maybe they're about the same distance away. But again, it's a really fascinating thing to see what these distances are, the differences in the distances, when you're kind of used to just seeing it as a picture on the sky. Now, I thought it's probably worth, after talking about the speed of light earlier, to mention that there is an exact speed of light to the nearest metre per second, and that's that number, 299,792,458. No more decimal places, it's exactly that. And it kind of seems weird maybe at first looking at that, how you could have such an amazing exact value for the speed of light in the universe. But it does come down to its definition. So there's nothing magical. It really comes down to what is a metre and what is a second. So very quickly, historically, the definition of a second used to be an average day divided by 86,400. But of course, what's an average day? No one's going to get that perfect. So in 1960, the length of the year was defined as the year 1900 divided by that big number to give us a second. But of course, even though it's now just 1 year, no one's really going to know how long 1900 was. So now the definition of a second is based on the cesium-133 atom. I won't go into the quantum mechanics of it, that's getting a little bit much, but essentially there is a property of the outer electron of the atom. It can have a spin relative to the nucleus. If the spin of the electron and the nucleus are opposite, it has lower energy. If they're the same, it has slightly higher energy. Now, the difference between the energy is the same as a photon with a frequency of that number. And so we can use that frequency, it's a bit more complicated than that, use that frequency so we can say that there are that many cycles, so when that many cycles of this photon are counted, we call that 1 second. So takeaway of that, not to worry too much about the figures, is that we can use the cesium-133 atom to get an exact value of the second to a very high precision. That's what they use in atomic clocks. So we now have a second, and that's going to be the same anywhere in the universe. So wherever you are, that's going to give the same result. So we don't have to worry about what the year was or what the average day was. We know what a second is. So with that, we can now look at the definition of a metre. It used to be the distance from the equator to the North Pole between Dunkirk and Barcelona divided by 10 million. Now again, that's not going to be exact. So then 1799 we had a prototype platinum metre bar. Of course, atoms can fall off the end, so if you wanted to get really precise, atoms falling off the end and heat changing the length is going to be a bit imprecise. 1983, the simple answer was to look at light, which is a constant anywhere in the universe, and we had our second. So just taking the distance that light travels in that portion of a second and calling that a metre gives an exact answer for a metre. So so if we look at what the previous metre was, and then we measure light travelling to a certain distance, and if we say the metre used to be around about there, then this gives us the closest value. So that is now an exact metre. So wherever you are in the universe, you can now, you don't have to remember the numbers of course, but you can now know that a metre and the speed of light are all exact due to definitions. It's not quite a circular argument, you'd think it was, but the fact that the second is defined by that cesium atom means that we're not defining a metre and the speed of light in a circular way. We've got the extra figure there as well. And so what that means is that we have our speed of light being exactly that because of its definition, but it also means we can define a light year exactly, because we say a Julian year for astronomy is 365 1/4 days. We can multiply that by the number of seconds, and then we can do a few bits of multiplication division, and we end up with a light year based on a year being exact and the speed of light being exact, and we now say a light year is exactly that figure. So a light year to the nearest 800 metres. So if you want to measure a light year exactly, you can now know that it's exact. Now we're not going to use that in everyday life, of course, but it means that if you're talking about light years and distances and the speed of light, at least everybody's talking about the same thing now. So the more precise measurements get, at least we can all know that we'll end up with the same answer. So that's just a bit of kind of fun facts for you there. And finally, just as we finish up, it's probably interesting to have a look at a comparison of the distances between the stars in the Southern Cross and the distances of the stars in Orion. So although they're in different directions in the sky, if you took them together, you can see that the Southern Cross stars and the Pointer stars are a lot closer than those stars of Orion. So that's the scale just moved next to each other. And it probably isn't right to stop without just looking at a couple of other things here. For example, if we look at Omega Centauri, a globular cluster, which is not far away from the Southern Cross, it's 17,700 light years away. The Jewel Box cluster, which a lot of you have probably seen through the telescope, 6,500 light years away. Our Pointer stars there. And now if we go over to 47 Tucanae, 14,500 light years, then way out to we'll go to the Large Magellanic Cloud, 161,000 light years. That's a dwarf galaxy of ours orbiting the Milky Way. And then out to the Small Magellanic Cloud at 203, roughly, 1,000 light years away. So I thought it's probably worth just showing those slightly more distant groups of stars, just to give a bit of a feel for where they are. So they're all kind of around the sky in the Southern Cross, those stars, and great to have a look at through a telescope. And that's how they would look pretty much through a good telescope. So we're pretty much near the end. So what have we learnt? Alpha and Beta Centauri. Beta Centauri about 80 times as far away as Alpha Centauri, and they're both triple star systems. So if that's all you want to remember for tonight, that's fine. I won't do a quiz. The main stars of the Southern Cross, quite a range of stars there. Two multiple star systems in the Southern Cross itself. So yeah, just remember a huge range of distances, and more than half the stars we see are multiple star systems. 300 to 400 billion stars in the Milky Way galaxy. We can only see about 2,500 with the naked eye from New Zealand as points of light, and there's a lot of multiple star systems. And now we know that the speed of light is about 300,000 kilometres per second, but if you want to know more, you know it's got an exact value, as has a light year. So I think it's probably worth finishing up now. Just leave that on the screen for you to have a look at and take in. And that brings us to the end of the talk tonight. Thank you. So any questions? Not that I could answer any more than probably what I've said, but if anyone's got a question, you're welcome to ask. I can try it. Or I can put you on to someone else who might know.
Oh, I've got a comment.
Yes.
I love the PowerPoint presentation.
Thank you.
It takes a lot of work. I do that too, but very, very simple. I appreciate just the time and effort and skill into doing that.
Thank you very much. Yeah.
It's amazing.
It's great to learn, isn't it, when you do all the pictures and the PowerPoints, so you learn yourself a lot from it.
Yes, but it's good visually for us.
Yeah,
I find that nice to follow.
Yeah, I think that's the thing about astronomy, we like to see the pictures, and astronomy is very visual. Yes. Usually, well, astrophysics not so much, but astronomy is very visual.
My other comment is that I've never liked constellations. It's just somebody's imagination. They're arbitrary. It's two-dimensional. Mm-hmm. Somebody else could join the dots in a different way.
Exactly.
It's like looking at the clouds and look, there's a rabbit.
Seeing the pictures of the clouds, exactly.
So I've never liked it.
Yeah, so if you want the Southern Kite from now on, you can use that.
So I wonder, have different civilizations join the dots in different ways?
Yeah, all around the world.
Okay.
I know in the Maori cultures, law, they have quite a few. I'm not aware of all of their images, but they have quite a different way of looking at it as well. So I think
the Australian Aboriginals have been looking at the sky for a lot longer.
Yeah.
So I've never looked at it. I might look it up later.
It is a good way for us to kind of remember them, because I think human brains like things to be a little bit random, and it's easier to remember. So it's got its pluses in that way.
But it's very two-dimensional.
But it is very two-dimensional.
The other thing I like about this, you've shown us that it's not.
Yes,
got depth.
and the depth is a really amazing thing to try and get your mind around.
Yes, that's good to think about. Thank you.
Yeah, thank you.
I think the way the Greek gods, they did do the constellations. I think it's an easy way for the general public to recognise them and have fun with looking at how the layout is. It's easy to understand for most people.
That's right. Yeah.
Right. Question. Well, Jonathn, I would like to thank you. Sorry, I was a little bit late coming over the Harbour Bridge. There was an incident on the bridge.
Yeah, no worries.
Otherwise, I would have introduced you. So, but thank you very, very much for coming all the way from Hamilton. Briefly, though, you mentioned quiz. It is quiz night next month, so we'll have some fun. So
I'll send you some of this. So you can put it on.
Yeah. So that'll be next month.
That now.
But otherwise, just from the gentleman's comment there, your graphics, I've always said they're just fantastic. They're second to none. So they're fantastic. We really appreciate you coming all the way from Hamilton for this talk. So thank you very much indeed. Thank you.
Say 500 to 1. Okay, it's